Welcome to the What You Can and Can't Learn from Petrography conference call. My name is Adrienne, and I'll be your operator for today's call. At this time, all participants are in a listen-only mode. Later, we'll conduct a question-and-answer session. During the question-and-answer session, if you have a question, please press star, then 1 on your touch-tone phone. Please note this conference is being recorded. I'll now turn the call over to Mark LaCuria and Kevin McDonald. Kevin, you may begin.
Terrific. Good afternoon. My name is Kevin McDonald. Mark Lucarilla is here, our petrographer. Yep. And we're from Baton Consulting Engineers, and we thought on a very brief discussion with Bev Garnett, we suggested that we've been talking about some of the issues that occur when you do petrography and how you can find some things out and other things cannot be determined by petrography, which went on to a discussion of why you shouldn't just use just a petrographer or just an engineer. And she asked us if we would do a webinar, and so here we are. So we have a lot of information to cover, and so I thought I would get started right away. So the first slide is a review from 10,000 feet. We all know that geology is a science, despite what they try to tell you on certain television programs. And engineering is not. Engineering is applied science. It's taking the real world, which is far too complicated to understand, and building a simple model so that we can predict the behavior of systems without having to construct them. And that's what we do with design and lots of other things. And if you're investigating an issue, neither is really sufficient on its own. And one of the things we want to talk about today, because we see it more and more in our practice, is a petrographer 10 or 5,000 miles away is sent a core and writes a report that details causes and effects without ever having seen the entirety of the structure. And that's really where we come down to what is it that happens in petrography, and what can they determine from just a core sent from miles away, and what they cannot. So the purpose of petrographic examination, from almost all of the time that you'll run into it as a contractor or as a design engineer, is to answer the question, what happened? Here's a perfect example. You can see there's some streaks and things in the snow. And if you look carefully, you have the track down here of a little rodent, and then you can see the wing marks and various things as the little rodent drove away. You have to infer that that's what's happening by doing investigation, looking at the wing paths of the bird, looking at the footprint of the animal, a bunch of things that that you're trying to tell a story about what must have happened in the background and what happened in the past. And petrography is no different. This is a local grocery store. I have no idea what transpired in that, who was blamed for what and what happened, but I can tell that there was in the past some type of a problem. That's the role of the petrographer engineering relationship, is to go and take a look. The real problem that we encounter is some things can be learned from the site, and some things can be learned and confirmed in many cases by microscopic examination, but there's much more to the world than exists under the microscope. I have a series of slides here. This is a slide from a pavement in northern Minnesota that is suffering a little bit of scaling, a loss of surface mortar. Mark's going to talk about that a little bit more. And so if this photograph is taken to illustrate a particular condition, cores would be taken so the petrography can confirm what might be the underlying cause. But the next slide shows the same pavement some distance away. And this is where you can start to get into trouble. The petrographers who looked at this originally took a core, a crack just like this one, saw that the crack had occurred early on in the age of the concrete, concluded that, well, the only thing that causes cracking early on in the age of the concrete must be shrinkage. Therefore, the joints must have been installed too late, or inadequately, and or that the shrinkage of the concrete is very high. And you can see about the middle of the page, there's a crack that jumps across the control joint. Obviously, that control joint was working, or else we wouldn't have that little jump that's occurring. But if we go further into the analysis and take a look and see what's happening, we find that an engineering analysis, just bending moments and bearing pressures and analyzing the slab as a beam on an elastic foundation, that in actual fact the pavement is inadequate. And it cracked early on because it was driven on at an age of about 12 days. And as a consequence, it's not capable of withstanding the garbage truck loads that it's seeing at an age of 28, or for that matter of any age, based on the strength that was available. So the petrographer, because the context is only the core, says, oh, early age cracking, that must be shrinkage. But in actual fact, a complete analysis, including some engineering analysis, shows that you cannot tell that, or you cannot, in fact, in this case, determine that it is a design error and not a construction defect at all. This is really relevant because if we look at the ACI documents, ACI 132 has a document written on responsibility in concrete construction. And it makes some very significant and I think important points on what the failure analysis process should look like. The first is that the failure analyst is supposed to act in an unbiased and objective way. They should not be advocates even when there's litigation going on. And they need to watch out for conflicts of interest. We routinely see petrographers whose lab division has worked on the project during construction have no problem in opining about whether the construction was performed properly or not. That's clearly a conflict of interest, as they don't know which side of the table to stand on. The other is reliability, and not an engineering reliability, but rather the reliability of the methods that are used. If I develop a method that only I can interpret the results of, and it's clear every time I do it what the interpretation is so long as you're me, I probably don't have the greatest reliable system. Scientific studies, which includes petrography, need to be repeatable, and they need to be well accepted and well understood very frequently. And Mark will talk about this. If you get someone who doesn't really know what they're doing and has access to, say, a diffraction camera or an X-ray fluorescence equipment or an electron microscope, they're going to start to see all sorts of things. They don't know what they're looking at, and they start to have problems. The other requirement is you have to look at what are the reasonable standards, whether they're cited in a specification, whether they're found in a code, or whether they're what the industry refers to as accepted industry methodology. If you're not aware of the way in which construction may be carried out with concrete, you can make errors if all you know is the geology of that concrete. And by the same token, if you look at concrete that is scaled, without a microscope, you really can't tell if the concrete was poorly air entrained, poorly finished, poorly proportioned, or poorly cured. All of those things need to be answered. There's a combination of factors, and in that combination, you really need two people. You need a petrographer, which we'll see a little bit more about a geologist, and you need an engineer to understand how the construction takes place. More and more frequently, we're dealing with problems for our clients where the petrographer has come in and talked about things that could not possibly have been executed by human beings, but without an understanding of construction, they have no idea what really has happened. And I'm going to give you a classic example. This is going back several years now. At least some of you on the call are contractors, and so you may imagine this sort of thing happening to you. And there's some text up from a petrographic report that you need to read. And I'll give you the context. Large international airport, taxiway replacement. The taxiway has a little bit of raveling going on some of the cracks. Talking to the contractor, it appears that there was a little bit of over-aggressive sawing. So it's a little bit of cracking perpendicular to the joints. The petrographer goes up, and or rather somebody goes up and takes cores and sends them to the petrographer. And they look under the microscope and say, oh, look, it's air entrained, but the air voids are all non-uniformly distributed. This is a great, terrible thing. No longer do we spend a lot of time talking about the joints. Now we're going to talk about the air voids. And I want you to read that upper sentence. The concrete does not meet the project specifications due to the non-uniform distribution of the air void system. There's no such requirement in the specification. You continue reading, you'll find out that you're supposed to uniformly mix in the admixtures, which is not really news, but there's a leap made, and that leap is that non-uniformly distributed air voids are a consequence of non-uniformly distributed air entraining agents, and that's simply not the case. Further, the investigator goes on to say that the concrete is not homogeneous, and it says right in the specification that it's supposed to be homogeneous. And therefore, since it is not homogeneous on a microscopic scale, it is in big problems. You can see we then talk about, again, about the raveling of the joints, but tie that into damage due to freezing and thawing. Again, restating the concrete doesn't meet the specification. The design engineer, who often is a generalist and certainly is not a concrete material specialist, reads this and says, oh, concrete doesn't meet the project specifications. It's time to remove and replace the entire taxiway at the airport to the tune of some $15 to $20 million worth of repair. And have the next slide, you can see, and I apologize, this is the best I have, and I've removed their names to protect the incompetent. This is their image. There's a 1 millimeter bar on the aggregate particle, and there is a circle all around a whole bunch of scary bubbles that are differentiated in someone's mind from the other bubbles. This is what they mean. They can say, well, if you look up here in the upper left-hand corner, there are not as many bubbles as there are in the middle. Therefore, the concrete is not homogeneous. In the presentation that I made for the contractor to the Airport Commission, I also pointed out that sometimes there's no air voids at all because there's big rocks, which also is inhomogeneous. But having read the specification, I realized that what they meant was the concrete had to be properly mixed at the macroscopic scale so that you didn't have sand streaking or large areas of segregated paste. Interestingly enough, the image in the corner is the same type of image from the Portland Cement Association. If you decide to get your pen out and draw little ellipses around things, you will find that there are areas that are highly concentrated with lots of air bubbles, like right here, and there's areas that are concentrated and they have a lot fewer air bubbles. This concrete is clearly also inhomogeneous, which of course it is intended to be. This slide, I believe, is something that was used in the 1950s during the development of explaining how air entraining agents work. Of course, for those of you who do a little bit of microscope work or who have ever been subjected to someone else's microscope work, you'll know that the average spacing factor or the mean spacing factor is the value that we want, the distance from any arbitrarily chosen point to the nearest air void. This type of inhomogeneity is normal. And so this is the problem that we get into. Someone who doesn't really know what they're doing and is completely trained in all the aspects of looking through the microscope at concrete, but doesn't understand how it gets put together, writes a letter like that that gets them ultimately gets the contractor up first in trouble because he had to hire lawyers and boring people like me, but ultimately does them no good. However, most engineers know very little about petrography, and most contractors as well. And so that's what we're planning on doing for the next 45 minutes, is to tell you why petrography is a useful tool. But keep in mind that it gives you lots and lots of information about the concrete that's present in the core. And it's only useful, it can only be expanded to concrete outside of the cylinder that's been, or the core that's been taken, or the cylinder, so long as the sampling has been done properly. And so frequently we fail in this particular case. If you go to a site and you select only the bad cores, and bad areas where you have poor performance, and you find there are orange aggregates there, you could conclude that the orange aggregates, which are always there when there's deterioration, are the cause of the deterioration. Without a control, without a sample taken in an area showing no deterioration, you can't be convinced that there weren't orange aggregates there as well. And it all comes down to the proper approach. Do we want to take an approach where we have a blank slate, as it were, with no presupposed conditions, to observe the natural phenomena, to develop a hypothesis, to test that hypothesis and develop a theory, an understanding of what may have gone wrong or what may have gone right, or the actual method that is sometimes preferred, at least in my experience, by some petrographers and forensic examinators, to draw conclusions because the client likes that, and then look around for evidence to support it. A very different approach. What you see up on the screen is a root cause analysis for concrete that is being scaled. And so if you take a look in the center, we have this one conclusion here. We have this one conclusion here. It starts out, my concrete is scaled. And you can go down through all of the reasons. Well, why did your concrete scale? Well, it was freezing with water on the surface and it was susceptible. Well, why was it freezing with water on the surface? It's either was salt exposure or freezing rain. Why was it susceptible? The water cement ratio too high, it's not air entrained, it's overworked, inexperienced finishers, rapid setting, someone used the wrong material, someone ordered the wrong material, someone made the wrong material. All of these are possible causes. One that we don't concentrate on very often is up here. Are you sure it's scaling due to freezing and thawing? And that depends on the diagnosis being made correctly from the data that's available and an experienced examiner. If you have a sulfate attack, if you have a salt attack that occurs, or even soft water attack that would occur in a place where there's never freezing and thawing, you can draw the conclusion that you have scaling due to freezing and thawing if the diagnosis is not done properly or the examiner is not experienced. And it's very important for us to end up in that position. So, one thing that the petrographer absolutely cannot do is tell you plastic or non-fundamental properties of the concrete. A perfect example is the slump. Slump is not a fundamental property. It's a property that changes with time. Strength is not a fundamental property. That's dependent on the geometry of the samples. But you can't look at the concrete and say that it was delivered in a blue truck any more than you could look at the concrete and say that it was delivered with a 7-inch slump. Water content and slump are long divorced and have been for at least a generation. You can't look at the concrete and determine that it has high or low shrinkage. You can infer that because you see a crack that is passing around the aggregate. And Mark will talk a little bit more about what that looks like. But in that sense, the slump can't be determined. The shrinkage can't be determined because shrinkage is a function of paste content, and actually more than paste content, just the water content. That's something you cannot get out of your petrographic examination. Some things you may or may not be able to answer. What age did the cracks occur? Because carbonation, as we're about to find out, proceeds at a known rate until it doesn't proceed anymore. And further, what was the cause of the crack? Frequently, the cause of the crack sits outside of that 4-inch or 3.5-inch diameter core. Perfect example, carbonation, which Mark's going to talk about how we diagnose it. It is an environmental effect. If your concrete is oven dry or your concrete is saturated surface dry or wetter than that, then air can't get in. In interior concrete, it is possible to use carbonation to determine the age of the concrete, so long as you don't have something like someone mopping that concrete floor once a week. For exterior concrete, a statistic that the European Code calls the time of wetness, which is how frequently it rains, issues will come and stop carbonation at some point. You need to remember that carbonation happens all the time to concretes that aren't wet all the way through, including at the surface. And in that intermittent zone, the rate of carbonation is dependent only on the temperature. Intermittent zone being where there's some drying. The other one that we see all of the time is crazing, a fine network of cracks. It gets blamed for all sorts of things. The concrete was crazed because it wasn't finished properly, because it wasn't cured properly, because it wasn't raised in a good home, whatever was wrong with it. Crazing is a consequence of carbonation shrinkage. It happens in all concrete. You can convince yourself of that by going outside after it has stopped raining and beginning to dry, and you'll find that almost every sidewalk is crazed because every sidewalk is outside. Engineering practice allows us to predict where to put the camera when we know that there's a bridge that's about to collapse. Durability, which is much more frequently encountering petrography, we're not always sure what happened. In this particular case, obviously the bridge has a case of giant gophers. And production records don't always help. These are bollards from near my mother's house in Canada. You can see that depending on which bollard you're using, you should or should not be using de-icing chemicals. The other thing to remember is that we make and consume and apply and install concrete in colossal volumes. This is an aggregate stockpile for 1 day's production of paving. If you take a core, you may have literally a handful of those particles. Very difficult with a single core to conclude something about all of that aggregate. Be careful. Causation and correlation is one of the greatest mistakes that are made. My wife teaches the second grade, and I like to remind her that if I take 100 random towns and plot the amount of alcohol consumed in a bar on Friday night versus the number of second grade teachers, I get a 1-to-1 relationship because they're both correlated. They're both caused by population, but they're correlated together, and you will get a very good agreement. That's not the same as one causes the other. We see colored concrete and freeze-thaw quite a bit. We see room temperature DEF being talked about. We see pop-outs in various places where they shouldn't be occurring. All of them require investigation. But as I turn things over to Mark to talk more about petrographic techniques, it is important to realize that when you're doing forensic analysis, assume when you hear horse beats that it's horses, not zebras. So Mark's going to talk a little bit about those techniques that are used and how we can keep things straight as to determining what we can and cannot tell you.
Okay. Good afternoon. Again, my name is Mark Lucarilla. I've been doing petrography for over 30 years. It's something that's kept my interest and for those 30 years. What is petrography? Well, it's not photography. That's a common thing I always hear. Well, you're a photographer? No, I'm a petrographer. So need to clear that up. Petrography, a good definition that I've found is a branch of geology, a general term for a systematic description of rocks based on observations in the field, on hand specimens, and particularly in thin sections. Now, concrete is essentially a man-made rock, and so we can treat it like a rock and examine it like a rock. In other words, we can make thin sections of it, and I'll show you the equipment that I use for that, and polish the hand specimens and take a look at it underneath the microscope. And there's a lot we can tell from this man-made rock we call concrete. And here again, just reiterating, cement, concrete, and mortar are essentially man-made rocks, therefore petrographic techniques can be used. The test methods that we use primarily are ASTM 295, which is petrographic analysis of aggregates for use in concrete. ASTM 856 is petrographic examination of concrete. ASTM 1324 is the petrographic examination for mortars. And ASTM 457 is the hardened air void analysis, which some of you are probably pretty familiar with. Basically, uses for petrographic analysis, troubleshooting, failure analysis, verify quality control, and research and development. And I'm going through these a little fast because I've got quite a few slides. I apologize. Petrographers are typically a geologist by education. There really is, not that I'm aware of, any school that teaches concrete petrography, so you have to learn under the tutelage of an experienced petrographer. It can also be a concrete technologist, and I've seen some that aren't geologists that are concrete technologists that do fairly well doing petrographic analyses, although they should have a little understanding of geology. Petrographers, together with an engineer that can interpret petrographic results, makes a dynamic team.
And for the reasons that we mentioned, and often the problems are related to macroscopic things that are not geologically related.
Correct. Petrographic analysis, see a brief history of the development. Petrography can be traced to the early part of the 20th century. Primarily, the U.S. Bureau of Public Roads and National Bureau or U.S. Bureau of Reclamation did a lot of work initially, in particular looking at alkali aggregate reactions, especially for the Bureau of Reclamation in dams where they used aggregates that were alkali reactive, and they wound up getting cracks and wanted to figure out why that happened. And they eventually figured that out, and then basically that kind of was the birth of petrographic analysis in the United States. Now, petrography is not always needed. The photograph on the left is a capped specimen, and here again, if we didn't have the cap when we received it was actually a core sample, we probably would spend a lot of time looking at other things to try to figure out why they had low strengths, and we did that anyway, but the fact that we had a cap helped us in our determination of why. Here again, you have this photograph on the right, which has a vertical crack going through the center of the core, which is usually indicative of a loading problem with the compressive strength test. And of course, you get the occasional footprint in the concrete. Basically, the perpetrator is probably about 6 feet tall, 240 pounds, and it was quite apparent what happened there. Basically, that's another shot of it. Yeah, okay, wearing size 11 work boots. I added that to it. And then every now and then, when you're in the wilderness in Colorado, you run across an odd shape. Perhaps a footprint. You can kind of see toes here and a heel there. Perhaps it's Bigfoot. Who knows? But you don't always need to do petrographic analysis. This particular one on the left, they had a lot of these. Initially got called out to look at this for a pop-out issue. And generally around here in Minnesota, you think of pop-outs being due to alkali silica reactive aggregates like opal and shales. I got out there and I could see that this was in a pattern, and it always happened in the same area. In the stamps, it was a stamped concrete, and we always saw it in that same corner, and then you come to where it stops, and then you see the offending material that was stuck on the bottom side of the stamp. So that really, you don't need to take core, you kind of know what happened there. Standard equipment that we use, basically, we've got some polishing equipment to polish hand specimens and to prepare the thin sections for making thin sections. This is a Petro thin, which is our equipment that we use for making thin sections. Basically, that involves cutting a rectangular billet out of the sample in an area of interest, cut it, polish it, epoxy impregnate it to stabilize the paste, allow that epoxy to cure, polish it again, and then glue it to a glass slide, and then cut it until it's, and do final polishing with it until it's about 20 microns or less in thickness. Think about it, the human hair is probably 70 or 80 microns in diameter, depending on the individual. And then we take, on the left side here is what thin section looks like during the preparation process. Okay, anyway, in the upper left-hand corner there you see what I was talking about as far as gluing the billet to the glass slide after it's been polished and epoxy impregnated and repolished. And then just to the right of that is a thin section, and if you go to the lower left part of the slide, you can see I'm holding up a thin section that's at its final thickness, and you can see through it, which means I can look at it underneath a polarized light microscope and pass light through it, and really look at the mineralogy of the man-made rock, if you will, and get an idea of how much residual Portland cement or fly ash is in there. And then I'll take a polished hand specimen, which you'll see here on the right, and look at it underneath the stereoscopic microscope. And there's a lot we can tell from that as well. My slides are a little jumbled around, I apologize for that. Basically, when you look at a thin section on the polarized light microscope, you have the one on the right here, which is in plain polarized light, and then on the left here we use we look at it in cross-polarized light, and that tells us a lot more about pastes and aggregates and identifying aggregates and hydration products that we might see, like portlandite or calcium hydroxide. Okay, this is sampling of cylinders. I'm not going to spend a lot of time on that. I've got a lot of slides here, but generally I'll go through these. I'll pop them up. I've got set for cores as well, and you'll be able to see where I like to take my samples from. Especially if you've got cracks and whatnot, you take thin section specimens out of areas of interest, especially where you got cracks. So basically take cores and thin sections from areas that represent the distressed and non-distressed concrete. That's usually helpful in helping you determine possible causal factors as to why it behaved the way it did. Sampling, we can take, usually we'll get maybe a chunk and we'll cut slices out of it, thin sections out of it, cement balls that come from a ready-mix truck or something, we'll take that and slice it and look at it. And then basically from fragments of mortars and whatnot. Okay.
You need to be careful in sampling as well. This is a core taken from a different airport and laid out with great care, and you can see here the core has been taken nicely. There's some nice, nicely cut in texture, and if you look at the core after it's been removed, the removal process has done some chipping. Without this initial photograph, you would think that there may be some spalls that are occurring in that pavement, all as a consequence of the sampling technique. There's other devices that we can use. We can look at a scanning electron microscope, and here you can see the neatest looking piece of concrete you can imagine. It looks more like a science fiction scape. Yeah. But we can start to look and see what is the mineralogical characteristics of an area. Similarly, we can run X-ray diffraction, which is a measure of the crystal properties of material, and start to make more more technological determinations of what the individual materials that we're seeing are. And these are useful tools in dealing with forensic problems. And there's lots of other things. Depending on the problem, you need to have a petrographer who is very well versed in all of the different techniques to look and see why a problem may be occurring. The natural rock, of course, is made up of aggregate.
And of course, you look at it using ASTM C295. Basically, we look for aggregate particles that would be alkali reactive, either alkali silica reactive or alkali carbonate reaction. Frost susceptible rock types, presence of clays, presence of sulfates, coatings, and dust on the aggregate size, shape, and then we report that. And then basically for alkali aggregate reactive aggregates, we look for such things as opal, like opaline shales that we have around in Minnesota, volcanic glasses, tridymite and cristobalite, calcinity, tripletic cherts, and even strained quartz can be considered alkaline reactive, depending on the amount of strain. Frost-susceptible aggregates, we look for clay-bearing rocks like shales and clay-bearing carbonates, weathered rocks, whether it be carbonates, granites, metamorphics, or cherts, bissel, which are easily split along closely spaced planes, friable rocks like sandstone chalk, rocks with high absorption, ferro dolomites, and iron oxides. Basically, frost-susceptible aggregates will cause deep cracking in concrete pavements and pop-outs on the surface. These are some examples of frost-susceptible aggregates here in Minnesota. The upper one on the left and the one on the right are actually rocks from my garden in the backyard. And you can see this is what we call an iron oxide, which is actually a weathered siderite. And then this is on the right is a opaline shale, and you can see how that has cleaved and broken apart. And then the lower left is basically showing you the iron oxide after it's been in concrete and has stalled. Decracking basically is either referred to as durability cracking or simply decracking, and basically it's characterized by a characteristic crack pattern that wraps around the joints, and usually the method of sampling is to take a sample away from the joint and a sample at the joint, and basically you'll see something like this, perhaps away from the joint, oops, on the left, there it is. You'll see cracks coming up from the bottom, and then as you get closer to the joint, you'll have cracks up near the surface, so you can see the typical profile of decracking, and that's not a very pleasant thing for many contractors or MnDOT or DOT personnel. And this is what frost-susceptible aggregate looks like. This is exhibiting what we typically refer to as a shattered pattern. Basically, the aggregate is shattered, and those fractures will extend into the paste and into the rest of the concrete and propagate towards us from a decracking issue in Iowa. Here again, as a consequence of being a petrographer, and Kevin does this as well, most concrete technologists do, you go to a gas station or what have you, and you're always looking down at the concrete and you see all these issues, and this one happens to be obvious frost-susceptible aggregates that have popped out of the surface. And usually that's associated with trying to force something like water through a pore or what have you that is smaller than what can accommodate that water that's moving through. Getting back to some sampling issues, especially with pop-outs, this is a random generated pattern for 5% particles. You can see, let's just say they're opaline shale particles. Basically, you can see 5% with a random pattern, you get quite a bit across the whole area. 2%, you start seeing areas where you have less and other areas where you have more. And it even becomes more apparent when you look at 1%. You have, and here again, this is a random generator. So basically, if you were to take a sample here, let's say, you can see that you have 2 pop-outs there. And when you send that to a petrographer, they might look at that and say, well, you got a lot of pop-outs, but actually there's a lot of space here and here and over here where you don't have much going on.
Yeah, and the great fault that people run into is they think that random processes should be uniformly random. It's quite clear that someone could consider the upper left-hand quadrant of that square to have something wrong with that particular load, but it's purely random.
Mm-hmm. And when we're looking at clays, basically, I like to use X-ray diffraction. Basically, this is a untreated clay, and then the same clay exposed to ethylene glycol vapors and then heated to 400 degrees centigrade. And basically, this pattern with all 3 together indicates to me that it's a bentonite clay, and basically that's the identification. Coatings and dust. Basically, this is in plain polarized light and thin section. You can see this is a coarse aggregate particle paste interface. This whole thing being this is a rather large coarse aggregate particle. But when you put it under cross-polarized light, basically you can see there's a little micro crack that runs right along that boundary, and then you can see a lot of dust that is adhering to that aggregate. And in this instance, anyway, it might indicate that you have a lessened paste aggregate bond due to the dust coating on the aggregate. Okay, and we'll talk a little bit about concrete petrography ASTM C856. Previously, we were just talking about the aggregates. Basically, we use concrete petrography to identify the causes of distress, like cracking, alkali-silica reaction, sulfate attack, chemical attack, freeze-thaw, damage, low strength issues, and then corrosion, especially spalling due to corrosion. Determine water cementitious ratio, and measure or estimate the hardened air content. I'll skip past this one. That was a kind of a duplicate slide. Alkali-silica reaction. This is from a pavement in New Mexico, and essentially, if you look closely, you can see all the map tracking in this. And so basically, core was extracted, and there's several methods we can use to look at it to positively identify alkali-silica reaction. One would be polished hand specimen, in which case you see aggregates with rims and gel. And then there's more, and then you can quarry out the gel and do a refractive index check on it, just make sure that it's alkali-silica reaction gel. And then basically use a scanning electron microscope to get the chemistry of the gel, which can tell you a lot. Usually it's rich with silica, and it will have either sodium or potassium. This one has both, which would be indicative of a expansive gel.
But that type of crazing you saw on the pavement could also be freezing and thawing, could be lots of other things, and this is one of the things that petrographer can tell you is exactly what the expansion is coming from.
And in this instance, you can see fractures coming out of the aggregate and going down into the paste, in which case you have gel plug in this area. And in thin section, you get the fractures going through, and then you also have a void here that is filled with alkali-silica.
And I don't know if our operator is still on, but we lost the signal.
I'm here. Did you want to go into question and answer, or?
No, we lost the signal.
The signal, the WebEx?
It says presenter view has been moved to presenter area only.
Okay, 1 second. Okay, we are working on it.
I can see.
Very positive.
All right, so if you guys can see the slides, we're going to keep going,
We'll keep
assuming
going.
that we can.
Okay.
If not, send in a question that says you can't. All right, so
Okay.
scaling is something we encounter fairly frequently.
Basically, you know, there are some definitions for the degree of scaling. You know, there's light scaling, medium scaling, severe scaling, and very severe scaling. And you can read that if you'd like, but we're going to move on in the interest of time. Light scaling looks something like this, where you have basically some of the paste has scaled off, if you will, exposing some of the fine aggregate. A lot of the coarse aggregate is still under the paste. Severe scaling will look more like this, where you've got the areas that are, where you've got coarse aggregate exposed and everything like that. So what will we look at when we're looking at it? So this is this is representative of the severe scaling photograph that you saw in the last slide. And one of the things we'll look for is, okay, is there proper air entrainment? And so basically we ran, you know, ASTM C457 spacing factors where it should be, and it's all the way up to the top, so it doesn't look like it was overly aggressively finished. So what next? So you look at water-cement ratio, and basically, that particular instance was found to be a higher water-cement ratio or higher water-to-cementitious ratio. Primary causes of scaling: low air content, high water-cementitious ratio, and aggressive finishing or early finishing. Air entrainment, I won't get into the history of that. Basically, you can read that if you like. On the left is an air entrained concrete. I think everyone has seen this, where you've got a lot of small air voids. Each division on the left is 1 millimeter. So that has a lot of entrained air, whereas on the photomicrograph on the right is what it looks like when there's very little air, perhaps 1%. Important air void parameters: total hardened air content, spacing factor should be 0.008 inches or less, and these are from ACI 201 recommendations. Of course, if you've had a chance to read Power's original paper on it, he said 0.01 or thereabouts. Specific surface should be greater than 600 inches squared per cubic inch. Air voids per inch should be 1.5 to 2 times the total air content. Water to cement ratio, basically water content divided by the cementitious content. Basically, we'll make thin sections. We'll look at the amount of unhydrated Portland cement left in the paste. And basically the one on the left has a lot of unhydrated Portland cement in it. You can see that unhydrated Portland cement clinker particles. There's quite a few. It's fairly thick with it. If you look on the one on the right, there's not as many. It looks more diluted and there's a lot of water. And then when you look at it in cross-polarized light, basically you see, it's hard to tell here, but you've got a lot of larger calcium hydroxide or portlandite crystals. Basically we look at, not only do we look at thin sections, because you can be fooled sometimes by thin sections, you also look at paste to aggregate bond when you hit it with a hammer. You look at the resulting fracture. Does it pass through or around aggregates or both? You look at the paste luster on the freshly fractured surface. You look at paste hardness. How easily can you scratch it with a dental pick? And then basically, if you're still not convinced what it is, you can do a water drop test. And if it soaks in right away, then you got a higher water cement ratio. If it takes 2 minutes or 3 minutes for it to absorb into the paste, then you've got a relatively dense paste, which would be more indicative of lower water cementitious ratio. Let's see. Okay, another interesting method would be Wood's metal intrusion porosimetry. Basically, these are the same magnification. We've just forced Wood's metal we've forced Wood's metal into the paste, and basically get an idea of what kind of porosity there is in the paste. And the Wood's metal under a scanning electron microscope will light up like you see on the right here. This one, it was a higher water cement ratio of 0.65 versus a 0.45. You can see the difference in porosity in the paste.
And Woods metal is a metal that has that's liquid in hot water, so we're able to push into the concrete without affecting it.
Okay, basically, you know, this is a core that we had received, and makes you wonder what went on there.
Yeah, that one, the proverbial water valve was stuck on.
Yeah.
You know, the other thing that we encounter quite a bit is shrinkage, and shrinkage is something that we can that causes cracking in concrete only if it's restrained. So frequently we run into these types of problems. We see plastic shrinkage, so you have some cracks that can be diagnosed looking at the structure but are confirmed by petrography. You can get an idea of plastic shrinkage is typically more along the lines of these cracks in this direction, cracks going in both directions is going to be something else, but these can all be confirmed as to the origin by petrography. Similarly, we have a very detailed up close. We can see a crack that is tapering off. The scale here, the scale on the side here is in millimeters. So we have a situation where we have very fine cracks. You can start to attribute as to what their cause is. Similarly, in this slide, we see a number of cracks throughout the concrete, some of which are passing through the aggregates, which tell us that they occur after the paste has gained some considerable strength. You can see here the crack passing through the aggregate, and here the crack is passing through the aggregate. These are useful devices to tell us something about the age of the crack, at least the age in terms of the strength gained from the concrete. Similarly, we can tell when water has been added at the site. You can see here in this notch, there's a darkened area of higher water to cement or low water cement ratio paste, and surrounding it is an area of high water cement ratio paste. We started with an example of people who couldn't tell what clustering is. That's an air void cluster associated with adding air and draining agent but not getting it fully mixed in. You can see there's lots and lots and lots and lots of bubbles here and hardly any around it. This is not going to give you a good spacing factor system. The difference between this and the slides we started out with are significant in that one of them is a defect and the other is not. Finishing leaves telltale signs in the concrete. We'll see blistering if we have concretes that are still bleeding or worse contain air. We can see that the finishing here at the surface, we have a densified layer of paste that is occurring due to the troweling. And if you look up here, there's a fracture in the paste. That fracture is occurring because of trapped bleed water. Here, the opposite. This is the surface, and the surface has been exposed to water. Higher water to cement ratio at the surface, not so much at the bottom. So you can use petrography to see whether you have finishing problems. We have people finishing either the naturally occurring bleed water or this gentleman who read the specification that said do not add water to the truck after batching, and he understood that both of these will result in this condition: high water content at the surface or water cement ratio, lower water to cement ratio further down. You can make a mistake. A colleague of ours many years ago identified this as a ASR pop-out. In actual fact, it's caused by a phenomena. You can see the little micro cracking all in here, where this particle has been torn and is free to move at the base because it's setting at the surface ahead of the rest.
And it was nicked by...
and the blade has picked it up and moved it around. And so we see that fairly frequently. Toppings can fail as well.
Yep, and basically, you can see on the left here, that's what the topping failure looked like, and basically, when you look at it in polished cross-section and also in thin section, you can see that, and this paste, this is concrete paste from the original top surface, and this is the topping. Detachment occurred within that top surface of the original concrete, and this was all carbonated, and so basically they likely did not remove the unsound concrete before they applied the topping.
Very useful in diagnosing problems.
Yes. Okay, thank you, and we'd be open to any questions.
Yeah, and I guess in conclusion, we wanted to show you that you can use petrography to tell you a lot of things. You can see what the water-cement ratio was, what the fabric was, how finishing affected the particle spacing and the water-cement ratio, how the aggregates packed together, where some cracks are running. But there are lots of things that without an engineering analysis you don't learn. All cracks that occur early on in the concrete are not caused by restrained shrinkage. Similarly, all pop-outs that have occurred are not necessarily subject to freezing and thawing. A lot of mistakes can be made if the petrographer is simply sent a core. You do need to spend some time doing an evaluation or doing an investigation to determine whether there are other exterior to the core issues which may be occurring. And then we'd be happy if the operator wants to open it up to answer any questions.
Thank you. We'll now begin the question and answer session. If you have a question, please press star, then 1 on your touch-tone phone. If you wish to be removed from the queue, please press the pound sign or the hash key. There'll be a delay before the first question is announced. Once again, if you have a question, please press star, then 1 on your touch-tone phone.
We were either very clear or very confusing.
And we have no audio questions at this time.
All right. Well, terrific.
Okay.
Well, thank you very much, everyone.
Yes, thank you.
And hopefully you have, unless you do petrography, a petrography-free day.
Thank you, ladies and gentlemen. This concludes today's conference. Thank you for participating, and you may now disconnect.